Imagine an entirely empty, infinite coordinate space. No matter, no particles, and no fields. In this context, infinity is not a specific number. It is a physical boundary so distant that an object located there feels absolutely no influence from our coordinate grid. We must also define work. In physics, work occurs when an external agent moves an object against an opposing force. If there is no force to push back, no work is performed. Our objective is to mathematically construct a system of stored electrical energy from scratch. We will bring in charges one by one to see how energy is calculated in a complex system. In a universe devoid of pre-existing fields, moving a single object from infinity to any location requires zero work. There is simply no force to overcome. This first charge, Q1, enters from infinity and settles at the origin. With no resistance, the external work counter remains at 0. While no work was done, its presence changes the grid, generating an invisible electric field that radiates outward. This single charge alters the geometry of the space, establishing a specific electric potential, or voltage, at every other point in the grid. The grid is no longer a void. If a second charge attempts to enter this territory, it will have to contend with the potential field Q1 has already established. The first charge possesses zero potential energy. However, its presence creates the electric potential that determines the energy of any subsequent charge brought into the system. As a second positive charge, Q2, is brought in from infinity, it encounters resistance. The two charges repel one another, and the external work counter begins to climb. To reach its final position, an external agent must apply a continuous force to overpower the repulsive electrostatic field generated by Q1. Because electrostatic force is conservative, the work performed by the external agent is not lost. It is stored entirely as potential energy within the spatial tension between the charges. This equation represents the mutual potential energy of the pair, directly proportional to the product of the charges and inversely proportional to the distance between them. Mutual potential energy is the total mechanical work required to force these two charges to occupy a specific, finite distance from one another. We can scale this rule by introducing a third charge, Q3, to our existing pair. As Q3 approaches, it overcomes Q1's field, storing energy along interaction R13. Simultaneously, it overcomes Q2's field, creating a second energy channel, R23. The equations merge, demonstrating the superposition principle. Total work is the sum of work against each field. This leads to the pairwise summation rule. The total energy of any electrostatic system is the sum of the potential energies of every unique interacting pair within it. We assembled this three-charge system in the order of 1, 2, then 3. But would the total stored energy change if we built it in a different sequence? In this split-screen comparison, timeline A follows our original order. In timeline B, we bring in Q3 first, followed by Q1, and finally Q2. Notice the intermediate steps. With only two charges on the grid, the work performed differs because the interacting pairs differ. However, once all three are in position, both timelines resolve to the exact same equation. Both require the same three pairwise interactions. This final result proves that electrostatic potential energy is a state function. A state function is a property that depends only on the final geometric arrangement of the system, not the path taken to reach it. Up to this point, we have only worked with positive charges. Factoring in negative charges changes the physical interaction. Bringing a negative charge toward a positive one requires negative work. Because the attractive field pulls the charge inward, an external agent must apply force in the opposite direction to prevent it from accelerating. This attractive interaction introduces a negative value into the pairwise equation, which reduces the total potential energy of the overall system. This duality means that like charges store energy when they are forced together, while opposite charges store energy when they are pulled apart. Consider this square configuration with a side length d. We have positive charges at the top left and bottom right corners, and negative charges at the remaining two. Our task is to calculate the total electrostatic energy stored within this entire four-charge structure. First, we examine the four outer sides. Each side connects a positive charge to a negative one, negative energy terms, all separated by the distance d. Next, we look at the two diagonal lines. These connect pairs of like charges, two positives and two negatives. These repelling pairs are separated by a longer distance, d times the square root of 2, yielding two positive energy terms. The total energy of the configuration is the algebraic sum of these 6 distinct pairs. The 4 negative attractions and 2 positive repulsions balance to determine the system's final energy state. One final question remains. How much work is required to place a new test charge, Q0, in the exact center of this square? These blue waves represent the positive electric potential radiating inward from the 2 positive corners, meeting at the center point, E. Simultaneously, the 2 negative corners project an equal amount of negative potential, represented here by these red waves, toward that same center point. Because the distance from the center to each corner is identical and the diagonal charges are perfectly opposite, the potentials cancel out. The net potential at the center is exactly 0, meaning no work is required to move a charge there. This architecture of potential energy is the direct result of geometry and charge. It is a strictly balanced mathematical sum that determines the total energy of the configuration.